In this video, we're going to look at a quick introduction to subrings. We're going to start with the basic definition. So the definition of a subring starts off with needing a ring. So we're going to let R under its plus and times be a ring. And we're going to let S be a non-empty subset of R. And we're going to say that if S, under the same operations that R uses, is a ring itself, then it makes sense to call S a subring. So we call S a subring of R, and we write S is a subring of R using the same kind of notation that we used for subgroups back in the first semester of modern algebra. In other words, we're just going to use the less than or equal to operator for meaning is a subring in this particular class. Now, it's important to realize that the operations that make S a ring have to be the same as the operations in R. So the operations in S are the same as the operations in the big ring R. Well, let's look at an example, and then we're going to look at a couple of properties. But it's important to look at examples. So let's look at a very basic example. If I take the set 2 times z, that's just the set of even integers. And if I think about how the even integers work, I know that addition and multiplication are closed on 2 times z, because if I add two even integers together, I get an even integer. If I multiply two even integers, I get an even integer. I also know that plus and times are both associative on 2z, and I know this because plus and times are associative on z itself. In other words, if I had problems with plus or times not being associative in 2z, then it couldn't be associative in z. So I know that they're going to be associative in 2z. Likewise, I know that plus is commutative inside 2z because plus is commutative in z itself. And I know that multiplication distributes over addition in z, and so that means multiplication distributes over plus inside 2z as well. Just a little vocabulary note before we go any further. We often say that the small set, in this case 2z, inherits, let's write that word right, That's still not writing right. So we often say that 2Z inherits associativity of plus and times, commutativity of plus as well as times, and the distributive law let's see, that can't be read very well, so the distributive law from the big set Z. And then we also now need to worry about additive identity element and additive inverses. Well, let's look at 0. I know that 0 inside of Z is an even number, and hence it belongs to 2Z. And I can prove that by simply observing that 0 is equal to 2 times 0. So we have an additive identity. And finally, I also know that if I take an even number and I look at its additive inverse, the additive inverse of an even number is also even, so minus a will also be in 2z. And so I know that 2z has additive inverses. And when we put all of this together, what we can conclude is that 2z, under ordinary addition and multiplication, is a ring in and of itself, and that means 2z is a subring of z because they're using the same operations.